In this video, we'll go over the practice test for induction. So just before we get started, make sure you do the whole test under a time limit, 70 minutes before using this video. You'll need these things. So you should have your graphics calculator, you should have your SACE formula sheet, which has lots of useful trig identities on there. And then you should have an A4 cheat sheet of your handwritten notes, single-sided. All right, so these are the performance standards we're being assessed on. First one is, do you know what you're talking about? Then can you use your calculator? Can you use good notation? And can you do proofs? So I'm hoping it does make sense that these are tested on an induction test. All right, first up we have our division. So it is use induction to prove that. So the very first thing we're going to have to do is let Pn be the statement that 9 to the n take 3 to the n is divisible by 6. And you don't write the for all n nz thing. All right, so for P1, we need to look at 9 to the 1, take 3 to the 1. Believe it or not, you get 6, which is divisible by 6. So therefore, P1 is true. All right, let's do PK now. Assume that 9 to the k take 3 to the k is divisible by 6. For some positive integer k. So k is in z plus, it's going to be a positive whole number. All right, therefore what that actually means is that 9 to the k take 3 to the k is a multiple of 6, so 6 times a, and a must be any whole number. And if we rearrange that, which is usually a good idea with these division proofs, 9 to the k is 6 to the a plus 3 to the k. Just like that. All right, now that we've got that, we can do pk plus 1. So we're going to be looking at 9 to the k plus 1 take 3 to the k plus 1. Now, we don't normally do a want to show for a division proof, but I will just do it here to make it extra clear. We want to show that it is divisible by 6. That's our goal. So let's see if we can do that. All right. We can split this up into 9 lots of 9 to the k, take 3 with 3 to the k. This is using our index laws. This is 9 lots of our star steps, so that's 6a plus 3 to the k. Take 3 lots of 3 to the k. So this is using star. So this is 54 lots of a plus 9 lots of 3 to the k. Take 3 lots of 3 to the k. This is expanding. And then this is 54a plus 6 lots of 3 to the k, which is collecting like terms. Now, I'm only being really finicky on explaining everything because we're doing a proof here. All right, and then this is 6 lots of, let's see, it would be 9a plus 3 to the k. And then this is factorizing. All right, last thing we need to do is explain why is this thing an integer. So 9a plus 3 to the k is in z as a is a whole number and k is a positive whole number. Now, really important that k is positive here, because if k was -1, we'd get a fraction for our answer, so it actually wouldn't be true. Therefore, pk plus 1 is true. And therefore, by induction, 9 to the n take, is it 6 to the n, I think? 3 to the n. Is divisible by 6 for all n in z plus. Just a little note about marks, you should be aiming for 1 mark every 70 seconds. So we're currently on pace, which is good news. Hence explain why that thing is divisible by 3. So 9 to the 10 take 3 to the 10 plus 3 is, now we can write this first thing as 6b from the proof that we did in part A. So it's 6 times something. So this is 3 lots of 2b plus 3. This thing here is a whole number, as b is a whole number. Now I should probably mention that b is a whole number there. And therefore 9 to the 10 take 3 to the 10 plus 3 is divisible by 3. Divisible by 3. I might just go like as required. So sometimes you can end proofs with as required or the little square. Depends on what your mood is. All right, let Pn be the statement. 5n cubed take 3n squared take 2n is divisible by 6. All right, P1. 5 lots of 1 cubed take 3 lots of 1 squared take 2 lots of 1 will actually give you 5 take 3 take 2, or in other words, that is 0. So yes, this is divisible by 6. Therefore, P1 is true. Now, it's probably worth mentioning in that previous proof as well, actually, that, so yes, this is divisible by 6. Just to be really clear why P1 is true. Cool. All right. So PK, let's assume. 5k cubed, take 3k squared, take 2k is divisible by 6. I'm going to assume that. For some k nz plus, so some whole number k. Therefore, we've learned that 5k cubed take 3k squared take 2k is 6 times some number a, and that a must be a whole number. Sort of means to be divisible by 6. Therefore, if we rearrange it, 5k cubed equals 6a plus 3k squared plus 2k. That is the thing that I'm going to label as star. Now, I've also noticed I hadn't labeled star in the previous question, so that's very important. All right, here we go. So let's do our pk plus 1 step. So we're looking at 5 lots of k plus 1 cubed, take 3 lots of k plus 1 squared, take 2 lots of k plus 1, and we can maybe expand that and deal with it. So I'm just going to do my equal sign down here just because it's going to get very messy. Something that could be good to have on a cheat sheet if you're not super familiar with these expansion rules are expanding squares. So that would be a squared plus 2ab plus b squared. And if it was a minus, you'd flick that one to a minus. A plus b cubed, a cubed, 3a squared b, 3ab squared. So those coefficients out the front come from Pascal's triangle, and then the powers of a drop and the powers of b go up. All right, you could have 4 and 5 on your cheat sheet if you want as well, if you want to be extra careful and you've got some room. All right, so let's expand this. It's k cubed, 3k squared times by 1, 3k times by 1 squared, and 1 cubed. This is going to be take 3, same thing, so k squared, 2k, and 1. And then we've got 2k plus 1 at the end. And then I might just make a little note, this is expanding. Now let's deal with this. So we're going to bring the 5 into each term. So 5k cubed, 15k squared. And then we've got, let's see, 15k, 5 take. Now let's expand the 3. So 3k squared, 6k, and 3. Take 2k, take 2. Be really careful when you're expanding in minus signs. You'll notice that the minus 3 flicked all those terms to minus. Same with the minus 2, flicked all the terms to minus. All right, we're going to collect our like terms. So our k cubed is just that term there. That's good. And then for our k² terms, we got that one, we got that one. So if we put those together, we've got 12k². For our k terms, we've got that one, and that one. So with our k terms there, let's see, that's 15, take 6, take 2, it'll be 7. And for our constants, they're actually going to cancel out. So we're going to have 5 minus 3 and minus 2, so that gives us nothing. So maybe I will sort of mark that on there, but yeah, nothing. All right, so just to be really clear about what we're doing here, this one here was expanding, and then this one here was like terms. All right, now we can use our star step. So we knew what 5k cubed was. It was 6a plus 3k² plus 2k. That's 5k cubed. I might actually keep that same underlining there just to be really clear. Then it's 12k² and 7k. So this is going to be using star. All right, so this is going to be 6a, we'll collect our like terms, so that's 15k² and 9k. And I'm going to leave the 6a there because that thing already is divisible by 6, that's good. And let's see if we can pull out 6 as a common factor from the last bit. We can't, is the short answer. But what we can do is pull out 3 and also k. So we're left with 5k for that first term, and then plus 3 for the next term. All right, so that wasn't quite the result we hoped for, but we are getting close. So what we can do is we can deal with this k bracket 5k plus 3 over here. So k bracket 5k plus 3. I'm going to split this into 2 cases. So if k is even and if k is odd. Now, if k is even, we have k lots of 5k plus 3 is an even times an odd. Turns out that will be odd, because if you think about it, 5k will be an even number, and then plus 3 flicks it back to odd. So that is even. And if k is odd, k lots of 5k plus 3 is going to be an odd times. Now this will be even at the end, because 5k plus 3, so 5k would give you the odd number, and 3 is an odd number, so you get odd plus odd in there, which is even. So it's even. So no matter what way you do it, you get an even result. Therefore, k, lots of 5k plus 3, is 2 times some whole number b. So I might just say like is even, just to be really clear. All right. Now what I might do is I might actually call this double star, or you can just draw an arrow when you deal with it or something like that. But essentially, here we can now replace this 3 times 2b. Now this is using double star. All right, cool. All right, so this is 6a plus 6b, which is 6 lots of a plus b. Now, a plus b is in z, as a is in z, and b is in z. Wonderful. Therefore, pk plus 1 is true. And therefore, by induction, we just need to take our original statement again and restate that. So 5n cubed 3, 2. Is divisible by 6 for all n in z plus. Little square there to end your proof. Good. I thought that one was nasty enough that I didn't give you the follow-up question. All right, question 3. So whenever I give you a table like this and part of it is filled in, it's a really good idea to make sure that you can replicate the working here. So what these sums mean is this one here, for example, would be 2 to the 1 plus 2 squared, which I'm hoping we can agree is 6. Now, you can do these on your calculators. Like if you wanted to get the next one, you can get 2 to the 1 plus 2 squared plus 2 cubed, and you would get 14 for the answer there. But that's going to take you a little while. And remember, one of the things that is being tested on this is, can you use technology? So do expect to have to use your calculators in developing some conjectures. Now, how do we do this a little bit quicker? Well, your calculator has a sum button. It's under math, and then it's in sum there. So we'll do that sum. It's going to be 2 to the power of x in the sum, and then it's going to go from x is 1 to, and then the number up the top will vary. So let's just check that we can verify all these sums first. So 1 to 1 did give us 2. 1 to 2 should give us 6. 1 to 3, which we just worked out, does give us 14. And then we'll go 1 to 4, should give us 30. And then if we look at this, 1 to 5 should give us 62. Wonderful. Develop a conjecture about the value of this sum. Now, for particularly an induction test, it's a very good idea to have some common patterns of numbers. So you might want on your cheat sheet all of your square numbers, so like 1, 4, 9, 16, all of your cube numbers, so like 1, 8, 27, 64, and then all of your powers of 2 and 3, so 1, 2, 4, 8, 16, and powers of 3 would be like 3, 9, 27, etc. So have all those patterns on your cheat sheet because they may help you spot conjectures. You might notice if you do have those that all these numbers here are 2 less than a power of 2. So in particular, 2 squared is 4, 2 cubed is 8, 2 to the 4 is 16. You're probably noticing here that no matter what number I pick here, it always works out. So 2 to the 6 is 64. So there's our conjecture. So our conjecture should be that I equals 1 to n of 2 to the I is 2 to the n take 2. Now I purposely made a mistake here. I want you to see if you can spot it before I tell you what the answer is. Pause the video if you need to. Alright, so the mistake that I've made is that notice n was 1 here and the power was 2. N was 2 and the power was 3. So what it should have been was n plus 1 on that power. All right, prove your conjecture is true using mathematical induction. Let Pn be the statement. It's a bit annoying that you do have to do this, but it's very important notation-wise. I equals 1 to n of 2 to the I is 2 to the n plus 1 take 2. So for P1, now that we're doing some inductions, we can start looking at the left-hand side and the right-hand side. All right, so the left-hand side is going to be I equals 1 to 1 of 2i, which is 2 to the 1, which is 2. And on the right-hand side, we're going to get 2 to the 1 plus 1 take 2, which is 2 squared take 2, which is 4 take 2, which is 2. So therefore, P1 is true, as they match. So I might just say tick and then match to make that very clear. PK. So we're going to say assume that PK is true. So I equals 1 up to k of 2 to the I is 2 to the k plus 1 take 2. We'll call that star, and then we'll say for some k in z plus PK plus 1. Now here's where we can finally do our want to shows properly. So over here we'll do a want to show. And the want to show is always what I'm hoping to end up getting on the right hand side. Or like it's the right hand side with k plus 1 instead of k. If you plug in k plus 1 here for k, you're actually going to get k plus 2 up as that power. Like that. So that's what we're aiming to get. Let's see if we can get it. So this sum here, I equals 1 up to k plus 1 of 2 to the I. We can split that. I equals 1 up to k, and I equals k plus 1 up to k plus 1. So this will be 2 to the k plus 1 take 2, and then plus, this will be 2 to the k plus 1 there. So this is using star on the left and then evaluating the sum on the right. So just to make it really clear, I might just, that was that bit, and that was that bit. So that's what both those pieces have become. My color coding here is just to help you really. When you're writing out the test, it's fine if you don't say which bit is which. That's all good. All right, so 2 lots of 2 to the k plus 1. We can combine those like terms. So I might just say here like terms. And then the next thing that I'm going to be doing is index laws to combine that power. So that'll be 2 to the k plus 2 take 2 as required. Therefore, p of k plus 1 is true. Therefore, by induction, I equals 1 up to n of 2 to the I is 2 to the n plus 1 take 2 for all n in z plus. Wonderful. All right, this induction here is absolutely brutal. I will not lie. It's a pretty horrible one, but we'll get through it. So pretty much what you need to do, we'll start, let Pn be the statement. One squared plus 2 squared plus all the way up to 2n squared is this horrible thing. Cool. Now, I want to do P1. We'll do the right-hand side first, just because I want to illustrate something. But then there is a very, very common mistake that you can make with this induction. All right, so the right-hand side is going to be 1, and it's 2 to the 1 plus 1, and it's 4 to the 1 plus 1. All over 3. So that is 1 times 3 times, let's see, 5. All over 3. So in other words, that is 5. Now, on the left-hand side, I will do the common mistake, and I want you to see if you can spot what it is. The left-hand side, so we're looking at P1, is 1 squared, which is 1, and they don't match. Now, let's look at some examples of n values, and then you'll hopefully see what went wrong here. So at n equals 1, my sum starts at 1 squared, and it has to end at 2 lots of 1 squared. 2 lots of 1 is 2. So the sum actually ends at 2 squared. When n equals 2, we start at 1 squared and we start churning through this, going through. It ends at 2n squared. 2n is 4. So that's the thing that's very weird about this induction. When you add, well, when you increase your n value by 1, you add 2 more terms, which we're not really used to seeing in induction proofs. But anyway, that will fix our P1 because it should have been 1 squared plus 2 squared, which is 5, and then they match. And then therefore, P1 is true. So I'm hoping that with this induction, although this is, in my opinion, probably the hardest induction on the pretest, you might actually spot that issue when you were doing your base case. And that's why doing the base case is very important. That's also why sometimes it's not a bad idea to actually prove P2 and P3 as well, just so that you sort of know how the pattern formula is going to work. Anyway, assume that all this Now, let's do our want to show. The kind of unfortunate thing about this induction is usually when we're doing a sum induction like this, we would really like to factorize and show that the factorized versions are equal to each other. Unfortunately, well, I've never managed to do this induction by factorizing, so I use something called the sledgehammer method on this induction. It's where you expand out both the left-hand side and the right-hand side, and you show the expanded versions are equal. That takes a little bit longer, but it is always a backup plan if you can't get the factorization to work. So the one to show on the right-hand side is going to be k plus 1, 2 lots of k plus 1, and 4 lots of k plus 1, all over 3. If we simplify this down, expanding that, you're going to get 2k plus 2 plus 1. So that'll be 2k plus 3. And then 4k plus 4 plus 1. So that is 4k plus 5. We'll leave that there because honestly, when you do this induction, you won't know already that you need to use the sledgehammer method. So let's work from our left-hand side now. And you'll see what happens. All right. So we got to have our sum. It's 1 squared plus 2 squared plus 2k squared plus 2 lots of k plus 1 squared. Now remember, when we have n go up by 1, we're bringing in 2 more terms to this sum. So this term here would be 2k plus 2 squared. This term here is just 2k squared. So I'm hoping it makes sense that the missing one in the middle of this would just be 2k plus 1 squared, like that. All right, now we can use star. So all of this stuff will become what we said it would be. 2k plus 1, 4k plus 1 over 3. And then this bit here, I'm just going to leave not expanded yet. 2k plus 1 squared and 2k plus 2 squared. And then this is using star. Might give myself a little bit more room here. All right, well, let's deal with this. The want to show has a 3 on the bottom, so that would suggest cross multiplying is a good idea. So we'll do that. When I cross multiply, this is going to get a 3 out the front of it. And this is going to get a 3 out the front of it as well. Cross multiply. Wonderful. Okay. Now, usually what you would do in an induction proof is you'd be pulling out factors. And the factors that you'd really like to pull out are factors that are in your want to show. Can I pull out a k plus 1? No. Can I pull out a 2k plus 3? No. Can I pull out a 4k plus 5? No. And that's why we have to use the sledgehammer method. I could maybe pull out 2k plus 1 from the first 2 terms and see what happens, but then I can't even pull that out from the third term. So let's expand it. K can stay out the front of this one. Inside the brackets, I'm going to get 8k squared. I'm going to get 2k, 4k, and 1. When you expand stuff like this, please leave the number out the front first. If you try and expand the 3 into here, it's actually incorrect because the bracket's sort of all locked in by that squared. And if you put the 3 in there, that's not mathematically valid. It's actually wrong. So you've got to expand it first, then put the 3 in. 4k squared, 4k, 1. 4k squared, 8k, and 4. If you're wondering what rules I'm using there, those are those perfect square expansion rules that we looked at earlier. Probably starting to see the usefulness of having that on your cheat sheet as well. All right, so this is expanding. Wonderful. All right, now let's factor everything in. 8k cubed. I'm going to combine those to a 6k. And when I pull the k in, it's going to be squared as well. Plus k. So that's going to be 12k squared, 12k and 3. And this is going to be 12k squared, 24k and 12. Wonderful. All right. Now we can start collecting like terms. So do I have k cubed terms? Yes, I do. 8k cubed. K squared, I've got 6, 12, and 12. That gives me 24 plus 6. That's 30. K terms, 1, 12, and 24. So that gives me 37. Constants, 3 and 12. So that's 15. One thing that I will point out, have we done the expansion right? One way that you can double check this is actually with your calculator. So this is a little bit cheeky doing it this way, but this is a cubic, so degree 3. And if I enter these coefficients, 8, 30, 37, and 15, and solve that, I get these 3 solutions. Notice these 3 solutions correspond to the brackets in our want to show. -1 for that one. This minus 1.25 is like 5 over 4, so that's the bracket over here. And this minus 1.5 is the bracket in the middle. So that tells us we're on the right track, that we've done this expansion correctly. So if I expand out the thing in the red, I should actually match what's in the black here. Let's try it. So FOIL out this, you're going to get k squared, 3k, 2k, and 3. So that's the first pair FOILed out. Only ever do them in pairs when you're foiling. Don't try and foil all 3 at once somehow. All right, if we do this, it's going to be k squared plus 5k plus 3. All right, now let's FOIL this stuff out. So I get k squared with 4k. So that's going to give me 4k cubed. I get k squared and 5. I get 5k with 4k. I get 5k with 5. I get 3 with 4k. And I get 3 with 5. Wonderful stuff. All right. Let's see. Now, I'm noticing a mistake already because we have 8k cubed in our want to show and I have 4k cubed here. So the issue was when I did this, we did most of that expansion correctly. Unfortunately, we missed the 2 in front of the k squared there. My apologies about that. That will affect these 2 terms. So that should be 8k cubed and that should be 10k squared. Wonderful. All right, let's try this. So if we collect like terms, that's going to be 8k cubed, 30k squared, 37k, and 15, all over 3. So wonderful, they match. That's good. Now, because this is a bit of a more complicated one, I might just draw the arrow to that. And let's say they match. And we're done. Therefore, P of k plus 1 is true. Therefore, by induction, then the whole statement. So 1 squared, 2 squared, 2n squared is that nasty, horrible thing. K, 2k plus 1, 4k plus 1. Oh, that should be with n's. 4n plus 1. For all n in z plus. All right. Now, this is a really good time to point out. Usually you can do part B's of questions even if you couldn't get part A correct. So if you don't get part A correct, you still have that induction proof here that you can use to talk about in part B. So please do part B even if you miss part A. And I'm assuming that a lot of people may have struggled with part A A anyway, so this could be a good strategy. If you did get part A, I'm very proud of you and your induction skills. So we've got to work out this sum. Now, basically this bit here, I need to think of as being like 2n squared. We need to think what would get us up to there. Well, the answer is essentially like, well, n would have to be 5 in this case. So that helps us. So if we look at our conjecture with n equals 5, that tells me that 1 squared plus 2 squared plus 2 lots of 5 squared has got to equal 5, 2 times 5 plus 1, 4 times 5 plus 1, all over 3. All right, now this gives you 5 times 11 times 21, all over 3. And that absolutely is something you can just work out on your calculator. All over 3 gives you 385. And then that would be 1, 4, and all the way up to 100 is 385. Therefore, the sum we actually want only starts at 4. It doesn't include the 1, but we can just take 1 off both sides. Take 1 and take 1. So you're going to get 384 over here. And on the left, we've got the sum that we want. All right, brilliant stuff. Consider this matrix, calculate a squared, show you working. So I want you to show you working for a squared here. Not to be nasty to you, but more just as a little refresher on matrix multiplication before you go and do the thing in the test. All right, 1 times 1 plus 1 times 1. Just being really clear about where all these things are coming from. This is 2, 2, 2, 2. Done. Calculate all those. You may use technology, and please use technology, because remember, part of what you're being assessed on this test is technology use, calculator stuff. So exit out here, go into matvict, then we're going to delete out whatever matrix we had in there. Yes is F1 there. Enter in, it's a 2 by 2 because it's a square matrix, 1, 1, 1, 1. Exit out of there, exit out of there. Shift, and then the mat button's over your 2. Alpha A, we'll just make sure we've entered it correctly. Yes, we have. So shift mat alpha A, we'll check that our squared one was correct first. Yes, it is. Now when we've done that, we can just go back and modify this. So A cubed is 4, 4, 4, 4. You may be spotting a pattern. A to the 4 is, I'm assuming 8, 8, 8, 8, but let's check. It is. And A to the 5 is, I'm going to hope, a whole bunch of 16s. Yes, it is. Conjecture. Let A equal 1, 1, 1, 1. Very important that you write this, because conjectures should be complete statements on their own. They shouldn't rely on the reader knowing some prior knowledge about A. Then, A to the n is 2 to the n in all spots. Now again, I've made a mistake on purpose. Pause the video, see if you can spot it. But this should have been 2 to the n, take 1 in all spots. Because when n is 3, you've got 2 squared, for example. Wonderful. Let Pn be the statement. A to the n is 2 to the n, take 1 in all spots. P1. On our left-hand side, A to the 1 is 1, 1, 1, 1. And on our right-hand side, we get 2 to the 1, take 1 in all spots. Cool. Therefore, P1 is true. Excellent. Now, assume a to the k is this. 2 to the k, take 1 in all spots. Star for some k and z plus. Cool. So let's look at p to the k plus 1. A to the k plus 1 equals. Now let's do our want to show. So for our want to show, or in other words, that is our right hand side of this equation, we would hope to get 2 to the k in all spots. A to the k plus 1, we split into a to the k times a. This is almost like index laws. Or like it's a matrix index laws essentially. So this is star, so 2 to the k take 1 in all spots. Times 1, 1, 1, 1. Using star. All right, if we expand this out and like multiply it, so it's 2 to the k take 1 plus 2 to the k take 1 in all spots. This is 2 lots of 2 to the k take 1 in all spots. And this is 2 to the k, 2 to the k, 2 to the k, and 2 to the k. Therefore, pk plus 1 is true. Therefore, by induction, a to the n is 2 to the n take 1 in all spots. Wonderful. For all n in z plus. Cool. Yeah, that's a good example for something that takes a lot of room in an induction proof because matrices are big. If you do end up using more space on something like a test, there's sometimes extra paper down here at the bottom, or sometimes you just need to attach it. If you do use extra paper, be sure to leave a note on the actual question itself as well, that you have used the extra paper. So that way your marker can see that. Don't just label, well, do label the extra paper as well, but make sure you label both. All right, we have a calculus induction, very fun. So just a reminder of our rules for differentiating exponentials. If y was e to the power of a function, dy dx is going to be the derivative of that function times e to the power of that function. This is the chain rule. So f dash of x is going to be the derivative of that stuff, so 2, like that, which is 6e to the 2x plus 1. There's some more derivatives. Develop a conjecture. So remember, conjectures have to be complete statements. Let f of x equal 3e to the 2x plus 1. Then fn of x, that's the nth derivative, is, all right, so what's happening, it's doubling each time. That's useful. So if we look at some patterns, we might have, I'm going to call f of x the same thing as f0 of x. This is essentially just 3e to the 2x plus 1. f1 of x is 2 times 3e to the 2x plus 1. F squared of it, like the second derivative, is 2 squared times 3e to the 2x plus 1, and you might be seeing the pattern. In fact, this is 2 to the 0 here. So fnx is just straight up 2ne times 3. I might put that in brackets just to be really clear. E to the 2x plus 1. I've bracketed the top of the thing there in writing the test, just so you don't accidentally think the one's hanging off the end. But when you're writing it in your proof, you don't necessarily need brackets around it. I would hate for you to accidentally get like not be able to do the proof because you're not having that brackets there. For all n in Z with n. Tell you what, I'm going to go from 0 this time, and we'll interpret like n equals 0 is just f of x. All right, and then you might actually just say this is the nth derivative, just to be really clear. The reason I'm going from 0 is I'm actually going to just emphasize a point that inductions don't actually always start from 1. Sometimes they can start from 0. In theory, they could start from anything. And if you Google around, there are some examples of inductions that don't work for like 1 and 2, but then they do work for 3 upwards. Anyway, let Pn be the statement. Fn of x is 2 to the n times 3e to the 2x plus 1. P1 or P0. So f0 of x is f of x, which is e to the 2x plus 1. Now this is on our left-hand side. On our right-hand side, this will be 2 to the 0 times 3e to the 2x plus 1, which is 1 times 3 e to the 2x plus 1. Oh, f should have had a 3 on there, which is 3e to the 2x plus 1, just like that. Cool. Therefore, P1 is true, because they match. PK. Assume fk of x is 2 to the k times 3 e to the 2x plus 1. Call that star for some k in z with k greater than or equal to 0. Remember, we're starting from 0 on this induction proof. Pk plus 1. So we would like to calculate f of k plus 1x, so the k plus 1th derivative. Now, there's 2 different notations that you can use for this. All right, there are 2 different notations that you can use for this. So one way that you can write it is by writing d over dx of fk of x. And that's probably the more preferred method. So this here is k derivatives, and this is one more. So it's like k plus 1. Anyway, if you do want some alternate notation, so you could have or fk dash of x, and that would be one more than fk. Anyway, let's do this. So this is going to be fk of x is 2 to the k times 3 e to the 2x plus 1. That is fk, and we're going to be differentiating that. So using star. So d by dx just means to differentiate something. So this is 2 lots of 2 to the k times 3 e to the 2x plus 1. And then you can say like rules of differentiation. And then that would be 2 to the k plus 1 times 3 e to the 2x plus 1. And then this can just be like your index laws. What were we wanting to show? We were wanting to show exactly this. So I want to show is 2 to the k plus 1 times 3 e to the 2x plus 1. So we've done it. All right. Then pk plus 1 is true. Therefore, by induction, fn of x is 2 to the n times 3 e to the 2x plus 1, just like that. All right, a trig induction. This is why it's very important to have our formula sheet of trig identities. This is a product induction, but be aware that trig can pop up in a lot of contexts, like matrices, for example. Also, this pretest does not have a normal product induction in it, so that could be worth practicing. All right, let Pn be the statement. All right, P1. So on our left-hand side here, we've got the product I is a 1 up to 1 of cos of 2ix. That's going to give us cos of 2x. And on our right-hand side, we've got sine of 1 plus 1x over 2 to the 1 sine of 2x. This is going to be, I might do the equal sign down here. This is going to be sine of 4x over 2 sine of 2x. All right, so the trig identity we've got to use is this one over here. Sine of 2a is 2 sine a cos a. And then really in particular, a is going to be 2x. And we're going to use that on the top. So on the top, that will split up this sine of 4x into 2 sine of 2x cos of 2x all over 2 sine of 2x there. We can cancel out the top and the bottom there and there. So the 2's and the sines. And what we're left with is what we want, cos of 2x. Now, how did I know to use that trig identity? Well, when we had this thing here, we saw that there were sines on the top and the bottom, and the final answer just had cos. So I was maybe looking for an identity to split the top into a cos and a sine, so that one of the sines would cancel off, and so that I'd be left with a cos on the top. And that's usually the strategy that you can use looking for identities. So P1 is true. All right, assume, so this is going to be PK. Assume the product I equals 1 up to k of cos of 2ix is, let's see, sine of 2k plus 1 all over 2k sine of 2x, just like that. We're going to call this star, and it's going to say for some k in z plus, just like that. Wonderful. All right. pk plus 1. Probably worth doing our want to show over here. So we like sine of 2k plus 2x over 2k plus 1 sine of 2x. Wonderful. Alrighty. So product I is 1 to k plus 1 of cos of 2ix. We split that product from 1 to k, and then k plus 1 up to k plus 1. Once we've done that, we can use star on the first thing. And then we can just evaluate this product here. All right, we don't need to cross multiply because we're already timesing the fraction. So I can just times the tops and the bottoms if you think of this one as being over 1, for example. 2 to the k sine of 2x in sine of 2 to the k plus 1x cos of 2 to the k plus 1x. Now the identity that we will want to use is the same identity as before. So this one where it says sine of 2a is 2 sine of a cos a. But we're going to use a rearranged version. Half sine of 2a is going to give us sine of a cos a. So we're going to use that on the top. And really particularly a is going to be 2 to the k plus 1x. Cool. All right. If we do that, on the top, we're going to get a half sine of, let's be very careful about this. So 2a would be 2 lots of 2 to the k plus 1x. And then this is over 2 to the k sine of 2x. You can actually think of this as like a half coming out the front. So this is a half times sine of 2 to the k plus 2x over 2 to the k sine of 2x, and then the 2's will times together because you got 1 over 2 there. So this is 2 to the k plus 1, sine of 2x, and this is sine of 2 to the k plus 2x. Therefore, pk plus 1 is true because that's what we were after, and I want to show. Therefore, by induction, product I equals 1 to n of cos of 2ix is sine of 2n plus 1x over 2n sine 2x for all n in z plus. Wonderful. Hence calculate that approximate value. So really you've just got to figure out what our x and the final n value should be. So this will be 2nx here. And then this one here, unless I've done that cheeky trick where I've lopped off the first value, this will be 2 to the 1 times x. So that would imply that x is 3. And then we can solve this one. So therefore, 2n times 3 is 192. Therefore, 2 to the n is 192 over 3. 64. And that gives us that n is 6. Let's check it. 2 to the power of 6 is 64. So, therefore, cos of 6 times cos of 12 times cos of 192 is going to equal sine of 2 to the power of 6 plus 1 times the x value is 3, and that is 2 to the power of 6 times sine of 2 times 3. All right. So this is sine of 384 on the top, and 2 to the 6 is 64, sine of 6. So we'll see what we get for this approximate value. Make sure you're in radians for this question, because I've specified radians over there. And we'll work out what the answer is. So that is going to give us sine of 384 on the top, and 64 times sine of 6. There we go. Minus 0.0371. All right, so we can actually double check whether or not this is right. Now, as far as I know, there's not really a product thing in the calculator that we can use, unless I'm missing it somewhere. But basically, you can just enter the product as is. So it was 2 to the 1 times 3 for that bit. And then we're going to be timesing by cos of 2 squared times 3. We're going to be going all the way up to 2 to the power of 6 here. All right, once you got that all entered in and you're still in radians, hit enter and you should get the same answer, which is good news for us. All right, Pascal's triangle. So this is an example of like a miscellaneous induction that you might see. So pretty much, so 1, 5, because 1 plus 4 is 5. 10, 4 plus 6, 10, 5, 1. 1, 6, 15, 20, 15, 6, 1. Now, once again, I've given you a table. When you see a table like this, you should always check the first few entries. So row 3 is going to be this one here. And if I add those numbers 1, 3, 3, and 1, I do get 8. Now be really careful with Pascal's triangle because this first row here is actually row 0. And then the next one is row 1 and so on. All right, if we add these 1, 4, 6, 4, and 1 gives us 16. Then the next one is 32. Then the next one will be 64 if you add them all up. Make a conjecture about how the row number relates. So sum of row n is 2 to the n. For all n in z, n greater than or equal to 0. Prove your conjecture using induction. So let Pn be the statement. Sum of row n is 2 to the n. And let's look at P0. So for P0, that's where we're starting. So the sum of row 0 is 1. statement. And then 2 to the 0 is 1, so tick, therefore P1 is true. PK. All right, now I'm going to be very careful about my notation here. Let row K be these numbers: A0, A1, A2, A, K take 1, all the way up to AK. Then we're going to assume that the sum of row K, so that's from I equals 0 up to K, of AI is 2 to the K for some K in Z. Now I might be really clear and just say the sum of row K is 2 to the K. So it's just a different way of saying it. It's still like what we do with division inductions. PK plus 1. We're going to have row K is A0, A1, A2, AK take 1, and AK. And then we're going to generate row K plus 1. Now, how do you do this? Well, you have out here a 1. Now, I want to make very clear that this 1 is also the same thing as writing A0, because A0 also equals 1 there, because any outside number there is 1. All right, if we keep going through, our next term is going to be A0 plus A1, so that'll be from those two. A1 plus A2. AK take 1 plus AK. And then the last term out here is AK. And again, I want to be very clear. This, the last term is sort of 1. But this 1 equals AK, because AK equals 1 there. All right, wonderful. So then the sum equals. Now I'm going to use the A0 version of this. So A0 plus A0 plus A1 plus A1 plus A2 plus dot dot dot. AK take 1 plus AK plus AK. So just be really clear where all those bits are coming from. Cool. All right. This, we've actually got 2 lots of everything. So this is 2 lots of A0 plus A1 plus AK, which is 2 lots of 2 to the K using star, which is 2 to the K plus 1. I didn't do a one to show, but had we done it, we would have said that it was 2 to the K plus 1 that we were trying to show. We've done it. Wonderful. Therefore, PK plus 1 is true. Therefore, by induction, sum of row n is 2 to the n for all n greater than or equal to 0. Wonderful.